Hey there, Mr. Sutton back again. We're going to take a look at one more take on graphing parabolas. This one is going to involve shifting a parent function. For your warm-up, go ahead and complete this function table for x squared, and then graph the function. Let's see what you came up with. So negative 2 squared, that's 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So negative 2 comma 4, negative 1, 1, 0, 0, 1, 1, and 2 comma 4. Parabola time. Now this is an example of something called a parent function. This is the most basic version of a function on which all the other versions of that function are based. So y equals x squared, that is your parabola parent function there. We're going to be working with parent functions through something called parabola vertex form. So I'm going to just show you this so you can see what it looks like. F of x equals a parentheses x minus h squared plus k. Now this craziness looks a lot different from the forms we've been working with, but it actually does have some cool advantages. One of them is that h comma k is the vertex. So if you see something in this form, you can pick out the vertex right away. This is the only time we've been able to do that. All the other forms, we had to do a lot of work to get the vertex. Now the vertex of the parent graph, this x squared looks completely different from this craziness down here. What we've really got is this is an x minus 0 squared, so your h value of 0. There's an invisible plus 0 out here, so your k value is 0. So that means your parent vertex is at 0, 0, which is about what it looks like in this graph. At this point, we're going to do a quick investigation as to what most of those letters in that vertex form actually do. We're not going to worry about the a value. We're just going to focus on h and k. Those are going to give us what are called translations. This is when you move or shift the graph without changing anything else. So there's a nice little GeoGebra website you can go to if you want and mess around with the h and k sliders. Again, that's the stuff that we're adding and subtracting to the parabola. Here's the website that I'm having you go to, and there's these h and k sliders you can play with. So take a look on there, pause the video, and see what happens when you do the following. Adding a number inside, subtracting a number inside the squared parentheses, and then doing the same thing outside. Or you can follow along with me, because I'm going to do this anyway. So let's see what happens when we add a number inside. So we're adding 4, 5, 6, 7. What's happening to our parabola as we add more and more numbers in here? Well, we're moving to the left. And let's see what happens when we subtract numbers inside. So I'll move my slider, and pay attention to this function here, because this, like h minus 1, h is already being subtracted from x in the normal vertex form. So if you want to subtract numbers, we need positive h values. Notice that when we subtract numbers, we're moving stuff to the right. So that's kind of weird, but it is what it is. Now let's see what happens when we do stuff outside the squared parentheses. So that would be the k value. If we add a number outside, now we're shifting the parabola up. And if we subtract a number outside, want to take a wild guess what that's going to do? You got it. Subtracting, subtracting, now we're subtracting. Now we're shifting our parabola down. So let's look at this pattern here. Inside was left-right changes, and adding made us go left, subtracting made us go right. That's kind of the opposite of what we expected. So we can draw the conclusion that inside changes are left-right and the opposite of what they look like. So these affect x values, and they do the exact reverse of what you think they're doing. When it looks like you're adding something to x, you're actually subtracting something. Now numbers outside, those affect the up-down, and they do exactly what it looks like they should. So if you're adding 5, for example, outside the squared parentheses, you are adding 5 to the y value. You're moving stuff up. We're going to take a look now at the process for performing translations using a table on something in vertex form. So first step to this, you want to make a table for the 5 points that go with that parent function, y equals x squared, And this is just all the x values from -2 to +2 and the y values that go with them. Do you have to use these x values and y values? Well, it's a good idea because this includes the vertex, which is really the most important part of the parabola. If you draw a piece of a parabola but you don't have that nice turnaround spot, you haven't really shown the reader much. Next step then, we're going to make a new table with the translation thrown into it. Now, when I make these tables, where I would put the x and the y, I put kind of rules for what I'm doing with x and y. Let's take a look at what's happening to our function here. We have subtraction outside the squared term. Outside changes, remember, affect y values. They're up, down, and they're exactly what they look like. Here then, this -4 outside means we are subtracting 4 from all the y values. So x is going to stay the same, but we're going to have y -4 in terms of what is happening to these original y values. Going through now, I'm going to go just column by column. X values are all going to stay the same, no changes there, but we're going to subtract 4 from all the y values. So this 4 is going to become a 0 in the new graph. 1 becomes -3, 0 becomes -4, and then we have -3 and positive 0, just plain old 0 again. Last step, plot the new points. So we've got -2, 0, -1, -3, 0, -4, 1, -3, and 2, 0. And graph the parabola. Now this has the advantage that you do all the really heavy mental lifting in this table, but once you've got it, the graph is just plotting these points that have been laid out for you. Disadvantage, of course, is that you have to mess with these tables. So there is a different way. We'll take a look at that now. Another method of doing transformations is to do it without a table. So this is a completely visual method. You start instead of making a table for the parent function, we're going to graph the parent function. So we've got -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Write out what's happening. So here we are shifting down 4. That's the same as subtracting 4 from all the y values. And then actually apply that change to each point of the parent function. So down 4. This one goes down 4. 0, 0 goes down 4. And the same thing for the other 2 points. And then reconnect the dots. So as you can see, this is a little bit faster because you don't have to mess around with tables. Downside of this is you're not showing really any work, so if you mess this up, there's really no room for partial credit. Another downside is going to come if you're trying to apply more than one transformation at once. Maybe you don't want to just shift things. Maybe you want to shift and reflect and stretch, and if you're doing all those things at once, then trying to keep track of all that visually is kind of a nightmare. So at some point, the table method is going to be pretty helpful, but if you're just shifting a parabola in one direction, maybe the visual method's a bit faster. For my part, for the remainder of this lesson, I'm going to do the table method. If you want to do the visual method, be my guest. So for this problem, -3 inside, that's a left-right change, so that's affecting x values. And remember, inside's opposite of what it looks like. So we're actually adding 3 to all the x values, not subtracting. So this is a shift to the right. Let's make a parent table here. And now the new table, my x values, I'm actually adding 3 to x, because again, it's opposite of what it looks like inside the parentheses. And then y is staying exactly the same. So new x values, we've got 1, 2, 3, yes, it keeps going like this, 4, and 5. I mean, all your x values are separated by only 1, right? So if you're adding the same thing to all of them, they should still only be separated by 1 at the end of this. Y values are all the same. So 4, 1, 0, 1, and 4. And graph it out. We've got 1, 4, 2, 1, 3, 0, 4, 1, and 5, 4. And parabola. We're going to do one more. Pause the video and try this one on your own. All right, let's see what we came up with for our changes. Inside change of a +1, that means we're actually going to subtract 1 from the x values. So we're shifting left by 1. outside change of plus 2, so we're shifting up 2, adding 2 to all the y values. Again, inside changes are opposite, outside changes are the same. So here's our parent table. Here's our new table now. We're doing x minus 1 and y plus 2. And this is where the table method starts to become helpful, again, when you're trying to do more than one thing at a time. You still could shift all of these parent dots by 1 to the left and 2 up, but this just makes it so much easier for me to see. So we've got -3, -2, -1, 0, and 1. And then adding 2 to all the y values, we've got 6, 3, 2, and then it repeats, 3 and 6. So we got -3, comma 6, -2, comma 3, -1, comma 2, and then 0, 3, and 1, 6. And draw the parabola. Now, as you're doing this, you should definitely check to make sure you're getting nice symmetrical points. If you're not, double check your table. Don't just blindly put in the points you've got in your table. It still has to look like a parabola. Well, that's it for this one. Hopefully nothing was lost in translation. Until next time, Mr. Sutton, signing off.